Hello, I'm Josh Damude, and welcome to the third lecture of Unit 3 of CSE 550 on network flows and matchings. In the last lecture, we set up the maximum flow problem. We defined it, we looked at all the notation we needed, and so on. In this lecture, what we're going to do is take that definition and formulate an LP for the maximum flow problem. And then we're going to derive its dual so that in the following lectures, we can work with the primal dual relationship of maximum flow. So just to remind us, the maximum flow problem as defined in the last lecture works on a directed graph G. It has special source and sink nodes S and T, and each of its edges has a capacity saying how much flow can be sent along any given edge. Given those things, the maximum flow problem asks us to find an ST flow of maximum value, where again, as a reminder, value is the net flow that makes it out of S, and the net flow that makes it into T. Either way you want to think about that from the perspective of S or the perspective of T is totally fine. They are always equal. So from this definition, we can very easily set up the following LP. We're actually going to work from bottom up because that's the easier way to think about this, starting with the variables. So what are the variables of our LP? They are the flow amounts that we assign to each edge. We know that those are always non-negative because the flow is mapping edges to non-negative real numbers. So of course, we have this very easy non-negativity constraint that comes straight out of that, and we have that for every single edge, little e in the edge set. The next thing we have are the edge capacity constraints. So you'll remember from the last lecture that we said for every flow, it cannot send more flow through an edge than we have capacity for. So, of course, we are just going to require that the flow value for an edge is at most C of E for all edges E. Okay, the other constraint we had was flow conservation. So you'll remember that this from the last lecture was about saying flow can neither be created nor destroyed. It is only distributed as it hits a node. So specifically, for all nodes that are not S and T, because remember, S and T actually are allowed to create and destroy flow, but for everybody else, we need it to be the case that the total flow coming into a node V is equal to the total flow leaving the node V. And remember again, delta minus tells us coming in, delta plus tells us going out. So those two things must be equal for flow conservation to work out. And then finally, perhaps the other really easy part of this is we want an ST flow of maximum value. So of course, this is a maximization problem because we're finding maximum flows. And this objective function that is written here is simply the mathematical definition of value that we had in the last slide. It's the net flow making its way out of S. All right, now there's an important observation about this LP. Not quite at the level of a lemma or theorem, so not really something we're proving, but an important observation. And that observation is that maximum flow always has a finite optimum. No matter how you set up the graph, what way the edges go, what those edge capacities are, and so on, we can always find an optimal maximum flow. And it's a real finite optimum. It's not something like it's unbounded and could be arbitrarily better. No, it is actually one real maximum flow that we can always go off and find. Why is this the case? Well, first of all, observe that if we combine these last two rows, what we are saying is every flow value, every variable, is bounded between 0 and the capacity, inclusive, right? So it can be any value between those, but it's locked in. Because of this, we know that that feasible region, that polytope that represents all of the possible solutions of the LP, is bounded. It does not go on forever because each variable has a bounded range. Excuse me, a bounded domain. We can also observe the following nice fact. If we just set 0 flow everywhere, well, this is probably not very good for our optimality, but it is feasible. Notice that, of course, 0 is in this domain, so we're fine with that. And also, if we put zeros in for flow conservation and we look at what happens, we're just adding up a bunch of zeros on the left-hand side and we're adding up a bunch of zeros on the right-hand side. So of course, 0 equals 0 whenever we need it to be. So flow conservation is satisfied, edge capacities are satisfied, and non-negativity is satisfied. So we conclude two things. Not only is the feasible region of the LP bounded, it is also non-empty. And any feasible region that is both bounded and non-empty has a finite optimum. So that's a nice observation that we're going to tuck away and use a little bit later. Now, the rest of this lecture is going to be about deriving the dual LP for maximum flow. What I want you to know is that if you have experienced some confusion or you get stuck in the details of this in these kinds of derivations that we've done before from primals to duals, then what you might want to do is pause this video, go ahead and watch the rest of the lectures about maximum flow and minimum cut, and then come back here. The reason that I say that is because this derivation is a little bit of a detour. I want you to see how it works. I think it's interesting and has some non-trivial pieces to it. But what you really need for future lectures to understand them is just the LP that we end up with at the end of this derivation. So you would be perfectly fine stopping here and moving on. But at least for those who are staying, we're going to go ahead and derive this dual. So this is the LP for maximum flow that we had on the previous slides. What we want to do is apply the primal dual algorithm to this. But in order to do that, we need this LP's dual. Now, something that's going to be a little different than, say, what we did for shortest path is that we usually start with a primal and then we derive its dual using the usual rules that we've been practicing for that. But actually, it's going to be easier for us in this maximum flow case to treat our starting point as the dual and work backwards to the primal. We'll see why in a little bit. But first, if that's the case, we need to get this LP for maximum flow looking more like a dual. So let's go ahead and do that. We already have a maximization objective function. That's what duals usually have, so we're good there. But we're going to do something that's going to look a little confusing at first, but it's going to make things easier for us in the long run. We're going to replace what this LP is maximizing with a new variable, which we're just going to call f star. Conceptually, you should think of f star as the value of the flow that we're building. But since we're getting rid of this nice formally defined objective function, we need two new constraints to relate this value variable, f star, to the net flow making it out of S, or the net flow making it into T. We actually need to give this variable meaning. So how we do that is we add two new constraints. The first one has this term here, which you'll recognize as the net flow making it out of S. We want that to be equal to f star. Why? Because f star is representing the value, and this is one way of thinking about the value, is the net flow making it out of S. So we want the difference between the net value making it out of S and the value variable to be 0. Likewise, from T's perspective, we want the net flow making it into T to be equal also to the value variable f star. So adding these two into our LP as new constraints will tell us that the value variable is always expressing what it should. All right, this one's much easier in comparison. We just want the right-hand sides to be numbers and not this whole summation thing going on. So we just move some terms around and we see that, okay, the flow making it out of V minus the flow making it into V must be 0. Why? Because flow conservation. All right, so with all of those things put together, we have the following LP that is written on the left-hand side. We're maximizing this new value variable. We have our two new constraints for S and for T. We have our flow conservation constraints here in the middle. And then the rest of these things are as they were before. We have edge capacities and we have non-negativity constraints where we've stuck in this new variable because of course we need that as well. So the rest of this is just going to be deriving the primal, right? We're going from dual to primal. So we're going to be deriving the primal LP on the right-hand side, one step at a time. As always, we need the primal's variables, objective function, and constraints. Let's start off by identifying the primal variables. Hopefully this is a broken record at this point and you know what I'm about to say, but a primal variable always comes from a dual constraint. So we need to look over at our dual and ask what the constraints look like. Well, first of all, if we look at these first 3 rows of constraints, you'll notice that we have one constraint for each node, right? We have a constraint for S, we have a constraint for T, and then we have a constraint for every node that's not S or T. So taken all together, of course, this is all of the nodes. So over on our primal side, we are going to introduce a variable xv for every node v in the graph. Moreover, you'll notice that these 3 types of node constraints in the dual all are equality. And that means that the corresponding primal variables should be unconstrained. This is just using our typical translation rules. But that's not all the dual constraint. That's not all of the dual constraints. The dual also has these edge capacity constraints, right? Here, there's one constraint per edge. So we also now need one primal variable per edge. These are inequality constraints, so the corresponding primal variables are non-negative. So that's good. That brings us to all of our primal variables. Now let's go ahead and do the primal objective function. So we know what the variables are. Now we just need to know the costs. Remember that the primal has an objective function where it's like the cost vector transpose times x. And in our situation, what that means is because we have some node variables and we also have some edge variables, there's 2 terms, and it looks like this. Just in case this is confusing to you, why am I writing cost instead of just C? We're used to looking this as C transpose X. I'm not writing C here because we're using C as the capacities of the edges, and I don't want there to be confusion. These are 2 different things. One is an edge capacity, one is a cost of a variable. So I'm going to use the word cost here. Okay, so we just need to know what the cost of each node and the cost of each edge is. Where do we get that? Well, we get that from the right-hand sides of the dual. Remember that primal costs become dual right-hand sides. And so we can easily recognize that here the right-hand sides for all the node constraints are 0. So the cost of all nodes is 0. And then the right-hand sides of the dual's edge capacity constraints is C of E. So we know that the cost of each edge in the primal is C of E. So plugging all that in, we have 0 cost times every node variable times capacity times every edge variable. Of course, the 0 makes this whole first term disappear, and we are left with minimizing the sum over all edges of the capacities that we're using. So every edge that is included in this thing we're building, we're paying its capacity. Okay, so we've got our variables, we've got our objective function. All that's left is we need to go off and get our primal constraints. Where do the primal constraints come from? Well, just like dual constraints gave us primal variables, well, primal constraints come from dual variables. What are the dual variables? Well, we've got these, right? We have a flow variable for every edge, and then we have the new variable that we added about the value. So those are our things. These are going to end up playing slightly different roles, so I put them in 2 different rows. We're going to have one set of constraints for all of the edges. We're going to have another constraint specifically for F star. Now, what are those? Oh, actually, before we actually talk about what they are, because these variables are all non-negative, we know that the primal constraints are inequalities. This comes from our usual rules of working from primals to duals. Okay, now we can go off and figure out what they are. The right-hand sides are easier. Remember that the right-hand sides of the primal constraints come from the dual's costs, and the dual objective function is very, very simple. It puts a cost of f prime or f star as 1, right? It's 1 times f star, and then there's nothing else there, so the other costs are 0. This maps over to here. The edges get 0 cost. F star gets a right-hand side of 1. The left-hand sides are the last thing we need to deal with here. So we're going to deal with it one dual variable at a time. When we're dealing with F star, we can ask the following question. What dual constraints does F star show up in? And when it does, what are the coefficients? Well, if we study our dual constraints, we see it only shows up twice. First, in the constraint for S, then in the constraint for T. And when it does so, it has a -1 and a +1. So when we translate this over to a constraint, we need the S variable and the T variable because we have the S constraint and the T constraint. And then we have correspondingly our -1 and our +1. So hopefully that's not too bad. Now we're dealing with the edges. That's the last thing we got to do, and then we're done. So where does edge UV appear? And when it does show up, what are its coefficients? Well, it actually shows up a handful of places, 3 places, and we need to deal with each of them. So first of all, this blue box. Edge UV, whenever it leaves node U, right? So it starts in U and ends somewhere else, that's going to have a +1, right? These are all the outgoing edges. So whenever an edge is leaving something, it has a +1. Likewise, whenever it comes into a node, it has a -1, right? All of these variables have a negative in front of them. So a given edge UV leaves node U with a +1, enters V with a -1. The last place we have to worry about it is in the edge constraints, right? So here, it simply shows up with a +1 coefficient in each edge capacity constraint. So translating that, it shows up in the node constraint for U, the node constraint for V, and the edge constraint for itself, for E. +1, -1, +1. All right. If you need to see that again, feel free to back up the video and watch it, but this concludes our derivation of the primal LP that corresponds to the dual for maximum flow. In the next lecture, we will look at what this primal LP actually means, and we will connect it to the minimum cut problem.